Hello. So we are going to talk about really section 7.6. We've shown a couple of different ways to sort of get an idea if your data set is normal by looking at the histogram. You can take a look at stem and leaf plots. But two ways that are used quite frequently are box and whisker plots and then the normal quantile plot or the normal probability plot. So I'm just going to draw a couple of box and whisker plots and sort of just identify them as normal or not normal. So if you have everything balanced in a box and whisker, then you're dealing with a symmetric distribution and you can argue it's normal. So if I were to sketch this and just sort of think about it as, well, most of the stuff's in the middle and then we kind of balance out that way, we're dealing with something that's reasonably symmetric, so we would argue that it's most likely normal. If, however, our tail went way out, like so, well, then we're dealing with the skew type situation. If our box is very close to one of the tails, and our center is kind of out of whack, so we have something of this nature where our median, forgive me, would be like here. Well, then you're dealing with something that's very tall in the middle, and then it sort of stretches out, so that we're looking at a skew type situation. And hopefully that makes sense, and hopefully you can look at a box and whisker and go, yeah, might be normal, might not be normal, very likely it's skew, that kind of thing. All right. So the next thing is the quantile plot or the normal quantile plot. And what happens, and I'm going to show you the process, but the basic idea is you're going to compare the z-score built off of a area, and then you're going to compare this z-score to what would be the z-score of these values. And if this z-score is close enough to how this would land if it was a z-score, then we end up with something that's fairly close to a straight line, and then we have a good idea that it's normal. So let's just start off, and this is how the approach goes. So this is your data point number. So 3 is our first data point, 3.3 is our second data point, 4.8 is our third data point, 5.9 is our fourth, and 7.8 is our fifth. Now there's a total of 5 data points. And so the way this works, and I'm not the person that came up with this, so I'm just repeating the process. The way this works is we take n to be 5, and we're going to go 1 over 2 divided by n. And since n is 5, 2 times 5 is 10, so we have 1/10. And so 0.1 is our first a sub I. Now, the next one we're going to do is 3 over, so we're counting up by odd values, 3 over 2 times n. So 3 over 2 times n is going to get us 0.3, and there is that one. There's our 0.3. And then we continue to do this. We do 5 over 2n, 7 over 2n, and then we finally get to the last one, which is 2n minus 1 over 2n. Well, that's going to be 2 times 5 minus 1 over 2 times 5, or you get 9/10, or what is 0.9. Now, how do you get these values? Well, we're going to use our INV norm, and we take INV norm, so second vars INV norm, 0.1, then 0, then 1, because the mean is 0, and the standard deviation 1 is on the standard normal curve, and we get negative 1.28. That's how we get this negative 1.28. Now we're going to do INV norm 0.3. So we're on the left-hand side of the normal curve. Our mean is 0, our standard deviation is 1, and we are taking up 0.3 of the area, and we're at negative 0.52. That's this one here. And so we're trying to get it, so is the spacing between these values matching basically the spacing between these values? and that's going to be able to determine whether we've got a straight line or not. All right, so we do that all the way till we get to the INV norm of 0.9, 0, and 1, and we get our 1.28. So what ends up happening is you plot the points 3, negative 1.28, 3.3, negative 0.052, or 0.52, forgive me, 4.8, 0. So you do the x sub I and the z sub I. So you put the x's along the x-axis and the z's along the y-axis. And so at 3, here's our 3, we are at negative 1.28. And you notice our scales are number line and then like thinking about it in terms of z-scores. So we have 3, negative 1.28. We are at 3.3, and then we're up to negative 0.05 or 0.52. And then at 4.8, which is almost 5, we're at 0. And then at 5.9, we are up at 0.52. And then at 7.8, we're all the way up to 1.28. And so this is reasonably close to a straight line. And so we would argue that our data is coming from a normal distribution. Okay? Hope that helps. Maybe I should just sketch one that's goofy looking and so you can kind of see. And I'll do that. Just let me put a cursor here, and I'll just move data down, and I'll go ahead and just scroll some stuff down. So things you're trying to not have happen, or you're hoping won't happen when you're looking at your data, is that you end up with, so you have this straight line, and you end up with something that looks like a horseshoe. That's a bad sign. That's a good indication that something is not normal. If you end up with like spiraling, probably not normal. Any type of patterning is a bad thing. You can have a little bit, but we tend to be concerned if there is much patterning or spiraling. We tend not to like stuff to tail off in one direction or another at the ends. In the middle, you kind of want it to hang in. And so you use this sort of, and it's really what's referred to as the 95% confidence interval range. And so you get this type of like interval, like as long as the dots are consistently in between these sort of hyperbolic looking spaces, as long as your dots are in there, you're most likely normal. It's okay to maybe get one outside of there, but if you have 2 or 3, you're starting to question whether or not normality applies. Okay. Again, hope that helps. I will stop the video and post it up now.